I'm Mackenzie Rosman, and I play Ruthie on the WB Seventh Heaven. I may not be an official treehouse detective yet, but on the show I love to help solve problems. No matter how difficult problems may seem, there's always a solution, and they're a lot easier to find using math, science, and technology. Stay tuned and help our treehouse detectives learn more about the future of transportation in the next exciting episode of the NASA Sci Files, the case of the radical ride.
Don't forget to look for the answers to the following questions. What invention led to man-made transportation? What is the first step in the engineering design process? The Channel Tunnel was a solution to what problem? When you see this icon, the answer is near.
You guys excited?
You bet.
Let's go.
Okay, 45 miles to the auditorium. Dr. D is traveling at about 55 miles an hour. Relatively light cargo. We should arrive at the awards ceremony with 5 minutes to spare.
Just enough time for you to work on your acceptance speech.
I would like to thank my mom and dad.
Not so fast. You are being awarded as a group.
Good point. Just try and keep it over 50, Dr. D. I don't want to be late, even if we don't win. Of course, drive safely.
Are you sure your calculations are correct? We might be cutting it a little close.
Why? Is the wind blowing? Dr. D, are you driving against the wind?
Don't worry. I think we'll be all right, as long as we don't hit traffic.
I know you wanted to get here early, but how long have you been here?
My mom dropped me off 20 minutes ago. We made really good time.
In that case, we should reconsider the minivan as the ultimate form of transportation.
Very funny. Our minivan is nice, but I wouldn't go so far as to say it's the ultimate form of transportation.
And even if it is advanced, it's not exactly futuristic like in the next century.
Which is our assignment.
So what do we do?
Let's open the problem board.
Good idea. So what do we know?
We know that transportation changes over time, and that it involves moving over air, sea, and land.
So what do we need to know?
We need to know how transportation will change in the next 100 years.
How do we figure that out?
History.
History?
Dr. D told us that history often tells us how things will work in the future.
So where do we go?
Well, for starters, I thought we should research the history of the car.
Why don't you check the internet? Maybe we can go to a car show and see one of those cool concept cars.
My thoughts exactly. In fact, Tony is visiting his family in Detroit. I'm sending him an email right now. Maybe he can visit the Walter P. Chrysler Museum.
Don't forget the concept car.
Right. I'm also sending an email to the other treehouse detectives to keep them updated.
And get their ideas. Speaking of the treehouse detectives, where are they?
Dr. D, if we don't start moving soon, we're going to have to average about 90 miles per hour to get there on time.
Sorry, kids, I don't know what the problem is.
The problem is, we need a helicopter.
I'm not sure that a helicopter would help us at this point. Hey, Bianca just sent us an email. She and Kaylee are working on a transportation assignment.
What is the assignment?
We're doing research on what transportation will look like 100 years from now.
Cool.
Bianca said that Tony's going to visit the Walter P. Chrysler Museum near Detroit, Michigan.
May I use the computer real quick? If Tony's checking out cars, I have a few questions for him to ask.
Sure. Remind him to get his Get Up and Go sheet from the NASA Sci Files website.
That's a good idea. You can always find great information and resources at the site.
Hi, Mr. Dressel. I'm Tony. Thanks for meeting with me.
My pleasure. How can I help you?
We're working on a school assignment researching what transportation will be like in 100 years. We thought the best place to start would be in the past.
That's a great place to begin.
Can you tell me when and where transportation began?
Well, the first form of transportation was by foot, or more commonly known as walking.
Yeah, I know all about walking.
At some point, boats were used and animals were domesticated. But the real transportation breakthrough hadn't happened quite yet.
Breakthrough? Like the invention of the driver's license?
Not quite yet. Archaeologists believe that the very first step towards man-made transportation began in either Mesopotamia or Asia, sometime around 4000 to 3500 BC, with the invention of the wheel.
Was the invention of the car next in the timeline?
Well, it was really the invention of the steam engine in the late 18th century that made mass transportation a standard. The early trains were slow and they were often very dangerous, but as locomotives improved, they really became important to our steadily growing and very young country, especially considering we didn't have a very good road system.
I understand how trains help people travel long distances, but how did people in the city get around?
Well, there was walking, and then there were horse cars and trolleys, and finally subways. But then in the 1880s and the 1890s, they discovered the bicycle, which was great because they could go where they wanted to and when they wanted to.
So they had wheels, but they didn't have wheels.
Right, they didn't have wheels as in cars.
Wasn't the car invented around the turn of the century?
Well, actually, in France, Nicolas Joseph Cugnot invented a car as early as 1769. But since it was powered by steam, most people don't consider it really an automobile. But in the 1880s, Gottlieb Daimler and Karl Benz in Germany invented a light, practical automobile engine that really ushered in the era of the modern automobile.
How has the car changed over time?
Well, this is a 1902 Rambler. It's basically a powered buggy built using the same sort of technology they used to build bicycles. And this is a 1915 Dodge. It's basically an improved version of the Model T Ford. It was a front-engine, rear-drive, open touring car intended for a rural market.
Why did the style of cars change?
In the 1920s, people's lifestyles began to change. We were no longer a country defined as rural, and people began demanding more comfortable cars. Take a look at this 1929 Nash. It shows the shift away from open cars. The car was no longer just a fair weather option. It was now a necessity, and therefore it needed to be enclosed.
Wow, this one looks different.
It's a 1934 Chrysler Airflow. It's the first mass-produced aerodynamic car design. By 1934, engineers had discovered just how much difference air resistance made on car performance.
We learned about airflow in the case of the challenging flight and how important it is on drag.
That's right, and airflows really changed the way cars looked.
Transportation has sure changed throughout history.
Yes, as transportation improves, it's easier to live and work farther apart. If you walk to work, you're not likely to live more than about a mile away from where you work. But if you've got a car, you can drive 30 or more miles to work.
And with the invention of the airplane in 1903 by the Wright Brothers, we can live even farther away and take vacations to faraway places. And thanks, Mr. Dressel. This has been a lot of help.
You're welcome. Feel free to enjoy the exhibits. There's a lot more to see.
I would never suggest breaking a law, but it looks like we will have to average about 227 miles per hour to make it to the ceremony on time.
I think you should check your numbers, Jacob. We should be fine. Remember, we have moved.
Well, Jacob does have a point. If we sit in traffic for very long, the car becomes useless.
What do you mean?
Well, no car can travel safely at 227 miles per hour.
Race cars can.
But not on the highway.
Good point, Catherine. Eventually you'll discover certain limitations to any technology. Look at all the different forms of transportation that have been invented over the years. For example, hot air balloons, helicopters, flying cars, my own personal hovercraft, skateboards, pogo sticks.
Wait a minute, Dr. D. Did you say your own personal hovercraft?
That's right.
Where did you buy a hovercraft?
I didn't buy it. I designed it and built it.
Wow, Dr. D. How did you build a hovercraft?
And did it take long to build?
Slow down, kids. Let me start by having you look at the device on the back seat. It's called a marble twister.
This doesn't look like a hovercraft.
Yeah, but it's pretty cool. What does it do?
Put a marble on the track at the top and tell me what you see.
It's going around in circles and gradually getting closer to the bottom.
Very good. The marble twister illustrates iteration.
What did you say?
Iteration. It's part of the engineering design process. It's like a cycle.
Wow, we've seen lots of cycles before, like the rock cycle and the water cycle.
In this cycle, you develop a plan for your project, design and build a model, test and evaluate the model, and then begin the cycle again by redesigning the model based upon your test results.
I get it. Then you test the redesigned model, evaluate the results, and redesign the model again.
That's just like the marbles. Each time you go around the cycle, you get closer to a finished product. Just like each time around the circle, the marbles get closer to the bottom.
How many times do you need to go through the cycle?
Well, the product is never perfect, so you just have to decide when it's close enough.
This engineering design process sounds an awful lot like the scientific method, except the step about identifying or recognizing a problem isn't included.
Actually, I just hadn't gotten to the first steps yet. In the engineering design process, the first step is called identifying a need or want.
Then you brainstorm ideas like we did in the invention process, in the case of the Wright invention.
Very good. The engineering design process is very similar to the invention process. After brainstorming, the next step is select a solution and do research.
And then you develop a plan.
That's it, and the cycle begins. Whenever you are facing a design challenge, the process we have just discussed will be very helpful.
I can't imagine a more difficult challenge than this traffic jam.
Trust me, Jacob, there have been bigger challenges.
I remember reading about the Channel Tunnel. They had all kinds of challenges to overcome to make it work.
Exactly.
What is the Channel Tunnel?
English and French worked together to build a tunnel under the English Channel. It is a major achievement in design for transportation.
Cool. Why don't you check the internet for it?
I'm way ahead of you. Working. Okay, here we go. Rosie and Wendy, Sci Files Kids Club members in the United Kingdom, have done their own investigation on the Channel Tunnel.
Awesome! The Treehouse Detectives have officially gone global.
Wow, this is incredible.
We're actually at the official nerve center of the Channel Tunnel.
Hello, we're looking for Mr. Storer.
That would be me. Hi, you must be Rosie and Wendy. I received your email. How may I help you?
We're investigating transportation.
And in our research, we learnt that advances in transportation usually result of having a problem.
And needing a solution.
The Channel Tunnel was definitely a solution to a very old problem. 13,000 years ago, Britain was connected to mainland Europe by a natural isthmus or land bridge. Then a change in sea level caused by the last ice age created the English Channel.
It seems we've had the technology to build tunnels for a long time. Why wasn't it built earlier?
2 centuries ago, Napoleon agreed that a tunnel should be built, but after war broke out between France and England, the tunnel idea was abandoned. Even though there were several plans for a tunnel, there were still technological problems to overcome.
What kind of problems?
At the time, people didn't know much about the geology under the English Channel, so they were unsure whether they could bore through it. There was also a ventilation problem.
How did they overcome the problem?
In the 1870s, both England and France agreed to work on a joint tunnel scheme. With government approval, the tunnel companies started on the first serious scientific geological exploration to find out just what kind of rocks are under the seabed.
What did they discover?
They found a bed of chalk marl which was perfect for a tunnel. It was easy to dig and impervious to water. It could also stand up without supporting walls and was thick enough to hold a tunnel.
So why didn't they dig the tunnel?
They made several attempts. In 1880, testing was carried out with a tunnel boring machine. The following year, another attempt was made, but abandoned again.
At least they kept trying.
Yes, finally in the 1980s, the British and French governments commissioned more studies and decided that a traditional rail tunnel would be the least risky and the best value for the money.
How long did it take to build?
About 7 years. The builders bored the tunnels from 1987 to 1991, and from 1991 to 1994, workers fitted out the tunnels and terminal. Would you like to see the tunnel?
That would be fantastic. This is amazing.
Why are there 3 tunnels?
Actually, there are 3 interconnected tubes. 2 are the rail tracks for going each way, plus 1 service tunnel used for maintenance and as a safe haven in case of emergencies.
Of course, you want to make the tunnel as safe as possible, especially for such a long tunnel.
How long is the tunnel?
It's about 50 kilometres total, with 37 kilometres underwater. Its average depth is about 40 metres under the seabed.
I imagine it took a lot of people to build something so complicated.
Yes, it took over 13,000 engineers, technicians and workers to build over 150 kilometres of tunnels.
That's remarkable.
Can you drive through the tunnel or do you have to take the train?
You can do both, sort of. Trains operated by Eurotunnel use the tunnel to carry cars, coaches, motorcycles, caravans and lorries. You just drive your car into the train and travel with your car through the tunnel. EWS carries containerised freight and the Eurostar trains carry foot passengers.
It seems like the Channel Tunnel handles all kinds of travelers and transportation.
Most definitely. In the past year, Eurotunnel carried over 2.25 million cars, about 70,000 coaches, and 1.6 million lorries. Eurostar carried 6.3 million passengers, and EWS carried 1.7 million tons of freight.
That's a lot of people and freight.
Correct. And with the opening of the tunnel, people can travel between Britain and mainland Europe any time of the day or night and in any kind of weather. It's now possible to have breakfast in London, lunch in Paris, and dinner in Barcelona, Spain.
It certainly makes the world seem smaller.
Not at this time, but Frank Davidson has a vision of a transatlantic tunnel someday.
A tunnel across the Atlantic Ocean? That would be impossible.
That might seem so now, but hundreds of years ago, so did the Channel Tunnel. Mr. Davidson proposes that a floating tunnel be anchored to the sea floor and a maglev train be used, travelling at speeds up to 5,000 miles an hour. You could literally live in the US and work in Europe.
Or live in Europe and work with the treehouse detectors during the day.
Thanks for the story, you have been most helpful.
You're welcome. Why don't we go and finish our ride through the tunnel?
Sure, sounds great. That's all for our investigation. Be sure and visit the NASA Sci Files website for more exciting adventures and scientific inquiry.
That was amazing. Talk about solving a major problem.
We could use a tunnel to get to the awards ceremony.
I just hope we make it.
Me too. We're running out of time.
So what's up? What's causing the traffic jam? How will the past help the detectives understand the future? Do you think Dr. D's hovercraft will be a success? Stay tuned for the next exciting chapter of The Case of the Radical Ride.
Don't forget to look for the answers to the following questions. Explain why research is such an important step in the engineering design process. Why is it important to build a model of your design? Why is it important to test your model?
I know that we're getting a lot done, but why did we have to be here so early?
You're kidding, right?
No, you're never this early for school.
I hope we'll finally get a chance to meet Mr. Gregory.
Mr. Gregory, the deputy administrator for NASA? He's coming here?
It's not every day you get the chance to win an award. It's even more rare to meet NASA VIPs.
I feel so underdressed.
You're fine. I hear he's pretty cool.
We should keep an eye out. What does he look like?
I don't know. I've never met him. But I heard he's supposed to be presenting today.
I'm just glad we got here early.
And on the topic of presenting, I just finished going over Tony's Get Up and Go sheet.
And
Tony hit a research gold mine. Not only did he go to the museum, but his aunt set him up with an expert at General Motors. I'm sending him questions now.
Cool. Guess the early bird does get the worm.
Very funny.
Thank you for meeting me.
Oh, not a problem. Your aunt was telling me about your assignment. She said you're doing research into future transportation?
Right, we're researching what transportation will look like in 100 years.
Well, I can't predict the future, but I can tell you it should be very exciting.
Wow, this is incredible! Are you accepting applications for test drivers?
Not exactly, but you can check it out.
What kind of car is this?
This is GM's Autonomy. It's a concept car designed around fuel cell and by-wire technology.
Fuel cell technology? What's a fuel cell?
Fuel cells are like batteries, except as long as they're fed fuel, they keep producing energy. They don't go flat or need recharging. This particular type of fuel cell converts hydrogen and oxygen into water and produces electricity and heat in the process.
So this car uses hydrogen for fuel instead of gasoline?
Yes, it does.
So how did you come up with the idea for the Autonomy?
Well, ideas for new vehicles can come from breakthroughs in technology, from formal processes like consumer research, or from very informal processes like discussions in the office, or even ideas that pop into your head while you're driving.
Sounds a lot like brainstorming.
It is. We brainstorm all the time. When we hear customers talk about what they love about their vehicle or what they wish it could do differently, it automatically makes us start thinking about solutions and new designs.
Dr. D told us about the design process. It seems like once you have brainstormed solutions for the problem, you have to do a lot of research.
It's really the scientific method in action. To develop an idea into a vehicle is really just a long series of solving problems. Before you can start solving those problems, you have to make sure you have all the data, knowledge, and information that you need. For example, I need to make sure I'm not violating any of the laws of physics.
So you have to know about things like gravity and friction.
That's right. And sometimes in the auto industry, we do consumer research to make sure that what we've designed is really what people want. One way to do that is to build a concept car.
So this is a concept car?
Right. A concept car is a one-of-a-kind vehicle that helps engineers and designers study and learn.
What have you learned from this concept car?
A lot. We learned that when you use fuel cells and by-wire technology to drive a vehicle, you no longer need an internal combustion engine, an automatic transmission, a gas tank, or any of the mechanical linkages that we have in cars today.
Those are really big parts that take up a lot of room. Without them, the car doesn't have to look the same anymore, and you're free to design it differently, inside and out.
Does it take a long time to develop a car from an idea to a real car that people can buy?
One of GM's concepts, the Pontiac Solstice, went from concept to production in just about 2 years, and that's really fast.
But with a really futuristic vehicle like the Autonomy, it's different. We're going to learn so much more before we're ready to produce it, so the first fuel cell vehicles that are sold probably won't look like this. It really depends on technology, on the purpose of the concept, and what the public thinks about it.
So not all concept cars are built?
That's right. It takes a lot of people, time, and money to build a concept vehicle. So we try to make sure that we build the ones that are the best use of our resources, the ones that are going to help us learn the most about technology, about our customers, and about our own capabilities.
It sounds like research is just as important in the design process as it is in the scientific method. Thank you. You've been very helpful.
You're welcome. And don't hesitate to call if you need anything.
So, can I borrow the keys to the Autonomy? For research.
Do you have a driver's license?
I'll have to get back to you on that one. In like 6 months.
Okay, Tony. Tell your aunt I said hello.
I will. Bye.
Wow, I wonder if Tony drove any of those cars.
I wonder if Dr. D will ever get to drive this van again. How's it going, Dr. D?
Slow, but I still think we'll make it.
I don't know. Award ceremonies aren't like movies where there's a bunch of previews at the beginning. But no pressure.
Pressure is actually a good thing.
Are you serious?
Remember, some of the best inventions have come from the pressure of having to solve a problem.
Well, we should do pretty well with the assignment because I'm definitely feeling the heat.
Wait a minute, Dr. D, you never told us about your hovercraft.
Oh, yes. Well, after brainstorming with 3 of the Sci Files Kids Club members in my lab last week, we decided upon hovercraft. Did some research on hovercraft to prepare for the design process.
What did you find out?
I discovered that the Navy has used hovercraft to transport up to 60 tons of cargo over both land and water.
Wow! There are 2,000 pounds in a ton. That is more than 120,000 pounds.
Very good. They can go up to speeds of 46 miles per hour with a full load. This requires engines with 16,000 horsepower.
That's a lot of horses.
I also did some research on air pressure. I needed to discover how powerful a blower I would need for an air supply and how big the craft would have to be to support my weight.
It's what you need to know, just like the problem board.
Precisely. I also found I needed to build a model of my hovercraft and test it to find the answers to all of my questions. I'm probably going to have to test and retest to refine my model before I actually build my prototype hovercraft.
Can we help?
Sure. Let's take a look at my first model. Based upon my research, I chose a round design covered in plastic. My research indicates I need a leaf blower to provide enough air for the full-size hovercraft. But for these models, I'm just going to use this vacuum cleaner.
You have holes in the plastic, but how do you know how many to make?
And how big to make them?
That's just the problem I'm working on right now. I'm testing several models to find just the right pattern and size for the holes. I'm going to test each model to see how much weight it can lift. Let's try it.
Why did you have to sometimes lift up the hovercraft?
Well, sometimes when the air is first turned on and the plastic is flat against the table, the air can't get out of the holes to start the lifting. I hadn't anticipated this problem.
I know. You could fasten something underneath the hovercraft that would give it a little lift to begin with. Then you wouldn't have to lift it up.
Excellent idea. Our modeling process is helping us to uncover and solve problems we didn't anticipate.
Are you also going to use different sized discs?
I sure am. In fact, that's my next step.
It sounds like building models of the hovercraft was really helpful.
It really was. Speaking of models, NASA builds lots of models for their designs. Why don't you visit their model shop and learn more about the modeling process?
Well, we're kind of stuck right now, Dr. D. I'll email RJ and ask him to visit the model shop. He can give us a report.
Great idea. I also think we should do more research on transportation.
Okay, email sent.
No rush. We have time.
Oh, cool. Dr. Textbook has a history of transportation.
I have to see this.
Hello! Dr. Textbook here. Have you ever wondered how birds fly? Well, that's exactly the question that Orville and Wilbur Wright pondered when they were trying to discover controlled flight. And it led them to this! An inner tube box? Well, you may say, Dr. Textbook, are you mad? What has an inner tube box got to do with the story of controlled flight? Well, the story is this. One day in their bicycle shop, the Wright brothers are talking to some clients, and they're playing with an inner tube box and twisting it back and forth. And one day, they suddenly realize, Eureka! This is it! This is the answer to our quest! Controlled flight! Get it? Well, in 1903, it was a very big year because in that year, the automobile made its first cross-country trip from San Francisco to New York City, and the Wright brothers made their historic first flight. You see, technology now has surpassed the expectations that the Wright brothers had for their aeroplane. Of course, we've all heard about NASA's HyperX plane. With its new technology, we'll all be able to fly much faster and more efficiently than this 1911 Model B aeroplane. With the next 100 years, innovative technology will make the skies the limit. Ooh. Just for fun, let's see how this 1911 Model B aeroplane fares in the skies with my hyper-realistic simulation of planes from the future! Not a very good idea.
I'm here at the NASA Langley Research Center's model shop to look into the design process involving models.
Hello, RJ. I read your friend's email, so I understand you want to learn more about making a model.
Yes. Now, we're doing an assignment on transportation and what it would look like in 100 years. Now, I understand that in the engineering design process that making a model is very important. I'm not exactly sure why.
Okay, say if you want to test your own design, would it be a good idea to just go and build it?
Probably not, because it'll cost too much. And you don't even know if it'll work.
Exactly. What if your plane or car doesn't work properly? Then you will also risk losing a human life during the testing phase.
Wow, I didn't think of that. But why are the models so small?
When we build model airplanes, the engineer determines what scale is needed.
What is scale?
Scale is the ratio or measure between the size of the model and the full-size version. For an example, take a look at this F-18 model. The scale is 5%, which simply means it's 1/20th of the full-size airplane.
So if an airplane is 10 meters long and I want to build a model about 1/10 its size, then the model would be about 1 meter for a scale of 1 to 10.
Very good.
What scales normally used when building models?
Well, one rule of thumb to follow is that the smaller the scale, the less expensive it is to build, and the easier it is to modify. However, the size varies depending on the design and how the model is tested in the various wind tunnels.
Aren't all wind tunnels the same?
Not at all. We have 38 wind tunnels, and they vary in size, and they test different functions. Some tunnels are large enough to test a small airplane, while others are only a few centimeters in size.
Why does NASA build airplane models?
Here at NASA Langley, we conduct research on model airplanes in order to make them safer, quieter, energy efficient, and more environmentally friendly. We also want to find ways to make them less expensive to build and maintain. Using models make this research easier and less costly.
Wow, that model over there looks really cool.
It's called the Blended Wing Body, BWB for short. It's a futuristic airplane with a unique shape that will cause the entire plane to generate lift and minimize drag.
We learned about lift and drag in the case of the challenging flight. They are two of the 4 forces of flight. If you want to learn more about flight, check out the NASA Sci Files website.
Very good. And the design of this airplane is more efficient and will consume 20% less fuel while cruising at high subsonic speeds.
Wow. It looks like the wingspan on this is about 88 centimeters, or 0.88 meters, on a scale of 1 to 100. So the full-size version is going to be 88 meters across. That's one huge plane.
It will be slightly less than the length of a football field. It's being developed to carry 800 passengers, but recent studies have focused on vehicles in the 450 passenger class. This model here is expected to fly the year 2020.
2020? Let me see, I'll be about 29 years old.
And I'll be... never mind.
Thanks, Mr. James. Never knew models would be so useful.
You're welcome, and I wish you good luck on your assignment.
All right, bye.
Bye-bye.
If those guys don't get here soon, they won't get a chance to enjoy the ceremony or meet Mr. Gregory.
According to the traffic webcams on the internet, the traffic situation's not good.
At least we're getting good feedback from RJ and Mr. James. I never knew model making was so important. What's next?
Time for the problem board.
So what do we know?
We know the changes in transportation are a result of new innovations and inventions.
And we know that inventions and innovations rely on research, designing, model building, and testing, all part of the engineering method.
Right, but we really haven't researched how you test your model yet.
Maybe the NASA Sci Files Kids Club could help. Do a search.
Will do. And yes, it looks like Cooper Elementary here in Hampton is working with King's Cross Education Action Zone in London on a design project.
London, Texas, right?
No, London, England. Both schools designed and built their own cars out of mousetraps, and now they're ready to discuss the test data. Hi, I'm Bianca Baker.
And I'm Kaylee.
Hello, good morning. I'm Jared, a 5th grader here at King's Cross Education Action Zone.
How's the video conference going?
Hi Bianca and Kaylee, I'm Kirsty. The video conference is very interesting.
This is our 2nd design meeting, and Mr. Logan from NASA Langley Research Centre is helping us with the challenge.
Right now we are reviewing our test results. Why don't you two join us?
Looking at the test data, it looks like you've made some great improvements. Does anybody have any problems that I can help you with?
Mr. Logan, this is Kirsty. The wheels on our car just seem to spin and the car doesn't go very far.
This is where the redesign process can really help improve your model. Think about redesigning your car so that the wheels get better traction. You might try testing different materials for your wheels. You have to balance the amount of friction you get with the weight you add to your car.
Sounds like it's time for redesign.
Exactly. Let me know what you come up with. Until next week, be sure to keep track of all your data and your trial notes.
What if we added balloons to the wheels? Would it add too much weight?
I don't think so. Actually, I think rubber bands might just work.
Sounds like a cool project, but what exactly is a mousetrap car?
It is a challenge to build a car using a mousetrap as the only form of propulsion. Our designs will be judged on the distance the car travels.
How did you begin?
We began by following the design process. Our teachers gave us a mousetrap car kit like this one and some other materials to work with. We looked over materials and brainstormed ideas. That's right. We decided we needed to do some research on energy, work, force and simple machines. Once we felt that our designs was going to work, we started building the model, but we had a problem when our axles wouldn't turn. We had trouble with our axles too.
After more research, we learned that the axle needed sanding. This helped reduce the amount of friction so that it could spin more easily.
What are you doing now?
We have been testing our cars to see how far they would go.
The first trial didn't go very well. The car only went 1 meter.
Our 2nd and 3rd trials weren't much better. We did have a few trials that went over 2 meters.
After 10 trials, we averaged 1.4 meters. We are hoping that the rubber bands will help.
Testing is really important in the design process.
Yes, it is. By conducting tests, we can see the problem before race day.
Of course, The trails that were over 2 meters were done at tire and carpet. That's it. The carpet added friction.
In that case, the rubber band should create enough friction to increase the distance.
Please excuse us, but we have to get to work right away.
Thanks for all the information and good luck in your competition. Be sure to post your results on the Sci Files Kids Club website. We want to know how it turns out.
We will. Bye from London.
Bye. Bye, and good luck on the challenge. Okay, so they researched their design, built models, tested the cars. What's next? Dr. D said the next step after testing and evaluation is redesign if necessary, which is exactly what the students are doing. I think we need to do more research on the redesign process and keep looking for Mr. Gregory.
So what's up? Will a new concept car be the answer to the detectives' problems? Why can't the detectives use Dr. D's hovercraft to get out of the traffic jam? Where should the treehouse detectives go next? Stay tuned for more of The Case of the Radical Ride.
Don't forget to look for the answers to the following questions. What is HyperX? What is a fault tree?
Dr. D, Bianca and Kaylee are doing research on the redesign process. Did you do any redesign work on your hovercraft?
Of course. It's actually a very important part of the design and invention process.
I remember from the case of the Wright invention that redesign is called the iterative process.
I wish your hovercraft was finished with the iterative process. We sure could use it right now.
Wouldn't work very well in this situation because it's electrically powered. You wouldn't get very far with an extension cord. It's one of the redesigns I'm working on.
So how is your project coming along?
Well, after testing our models for some time, we came up with a design for a prototype or a full-size model. Our testing helped us find the proper size and pattern for the holes on the bottom.
When we redesigned the models, they kept getting better and better.
That's iteration. I helped test the airflow from the leaf blower, and I think we'll have plenty of air pressure.
This plastic lid on the bottom, which was Jared's idea, helps us overcome the starting problem. Now it's time to test the prototype.
Don't forget your crash helmet, Dr. D.
And your elbow pads. And while we're talking about safety, let's put on some ear protection. This leaf blower is pretty loud. All right, the research was right on target. It really works.
This looks like fun. Can I try too?
Sure, go right ahead.
Is it time now to tell others about our success? It's part of the design process, isn't it?
You're right. But what do you think is the best way to do that?
Wait a minute, Dr. D. It seems to me that we still have a major problem with the system.
What do you mean?
Well, shouldn't there be a way to move around without being pushed?
I guess you're right. Aha! It's time to start the process all over again.
Oh, I see. We've identified a need. Now it's time to brainstorm.
How about we use a rocket engine?
I like the idea of a fan, like the swamp boats in Florida.
How about 2 fans mounted on brackets?
Shouldn't we get rid of these power cords?
Let's just handle one problem at a time.
Okay, Dr. D, I vote for the 2 fans.
No, I like the rocket engine. It would really...
Okay, wait a minute. It's time for me to pick a solution, do some research, come up with a plan, and design and build another model. There's a lot of testing to do before you finally reach your goal.
This iterative process of design, testing, and evaluation and redesign is pretty cool.
You bet.
Hey! I just got an email from RJ about the HyperX.
That sounds really high-tech.
I'm sure it is. Mr. James told RJ that the HyperX is in the middle of the redesign process right now. He's on his way to meet with Mr. Robinson to check it out.
I'm impressed. For being stuck in traffic, you guys are getting a lot of work done.
Yes, we are good at multitasking. Now, if only there's a live broadcast of the ceremony over the internet, then we might not miss it.
Now I'm getting nervous, Jacob. Hopefully we'll still make it.
Mr. Robinson?
Hi, RJ. What can I help you with today?
We're working on a school assignment to figure out what transportation will look like in 100 years.
Wow, that's a tough assignment.
We learned all about identifying problems, creating solutions, building models, and testing and evaluating data, which is all part of the engineering method.
Sounds like you have a really good handle on the process.
Thanks. but we need to learn more about what you do when the test results don't turn out as you expected.
Well, I can certainly tell you about that. We've been working on a program for about 8 years called HyperX. Although it's been very successful, we have had test results that were not always favorable.
What's the HyperX program?
Well, it's a series of small experimental research aircraft. Each one's about the size of a small car, and it's designed to test a new type of propulsion system called a scramjet.
How does it work?
But for a scramjet to work, the engine and the vehicle it's attached to must already be flying at a pretty fast speed, around Mach 3.
Mach 3? That's 3 times faster than the speed of sound. We learned in the case of the barking dog that sound travels at 330 meters per second. Times 3? That's 990 meters per second. Now that's fast.
Yes, it is. The engine uses the speed of the aircraft and its special shape to compress the air. Once the air is compressed, fuel is mixed in and burned, much like in a car engine, but with a lot less moving parts. The fuel-air mixture is then expanded out the back of the engine, and it propels the vehicle forward.
What are the benefits of using a scramjet rather than a regular engine?
Well, if you use a scramjet on a spacecraft, you don't have to carry as much oxygen on board as you do with today's conventional rockets. This would allow the vehicle to be lighter, safer, and less expensive. You can carry more cargo and payload to space.
Could it be used on a regular aircraft?
Yes, if we can successfully demonstrate this technology, it could allow us to build a whole new generation of aircraft. We could take off from the United States and fly to Japan in 2 hours. Today that trip takes 14.
Now that's the plane of the future. Now, you said the HyperX had problems. What were they?
Well, on our first flight attempt, we had a problem with the booster rocket that's supposed to get us up to our test condition at Mach 7. About 13 seconds into the flight, the wings and tails broke off the vehicle and it started to lose control, and we had to destroy it. We were all very disappointed. The scramjet didn't even get a chance to work.
That must have been awful. What'd you do?
Well, we made a list of everything that we thought could have gone wrong and what may have caused it. This list is called a fault tree. We studied each branch of the fault tree until we could eliminate that branch as a contributor to the failure.
Did you find the problem?
Well, the branches that were left on the fault tree were investigated further. We redesigned some of the parts and changed the way we fly the rocket. And after 3 years, we think we're ready to fly again.
Sounds like a complicated process.
It is, and it takes time, but you really have to do a thorough job when test results aren't what you expect, just to prevent future problems.
Thanks, Mr. Robinson. You've given me a lot of information on the redesign process. Good luck on your next test flight.
Thank you, RJ, and good luck on your assignment.
Right.
Call if you have any questions.
Thank you.
I hope the traffic clears up quickly.
How much time do we have?
The auditorium doors will open in about 30 minutes.
At least we'll get good seats.
I'm not worried about us. Great! It looks like RJ spoke with the HyperX people.
Do they have a solution for the traffic?
No, but they will eventually change the way we travel.
And that's a good thing. Now we've looked at design, testing, and redesign. Where do we go next?
How about the problem board?
Great. What do we know?
We know that transportation has changed radically over time.
Right. Planes, trains, and even cars look and operate more efficiently than they did 20 years ago.
We also know that the design and redesigning process is critical to making these improvements.
So what do we need to know?
We still need to know what transportation will look like 100 years from now.
That is our assignment. And boy, is it tough. From everything we've learned so far, who knows? We may not even use trains in the future.
Hold on, Kaylee. Don't forget what we learned at the Channel Tunnel. Trains have made some big improvements over the years.
You're right. I guess I just haven't ridden on a train in a while.
As a matter of fact, I did some research on maglev trains. I'll try to bring it up. I also saw in Tony's email that a NASA Sci Files Kids Club in Detroit, Michigan is doing an experiment with maglev technology.
Awesome, we can check it out.
Here it is.
Hi, I'm Jamon. And I'm Antoinette. And we're in Miss Thomas's class at Golightly Educational Center in Detroit, Michigan. We're working on an experiment using magnets with our mentors from the Society of Women Engineers. We saw Wendy and Rosie's report on the possibility of a transatlantic tunnel, and we wanted to know how a maglev train works. So we did a little research and decided to investigate magnetic field strength. We placed 4 magnets on the wooden dowel with the opposite poles together so that the magnets would stick. Then we added the 5th magnet on top with the same poles together so that it was repelled by the other 4. We used a metric ruler to measure the distance between the top magnet and the ones on the bottom. Then we added 2 washers at a time onto the top magnet and measured the new distances. Then after 10 washers, we began adding them 4 at a time. After each measurement, we recorded the distance in millimeters on a chart. We also put the data on a graph that had the number of washers on the horizontal axis and the distance on the vertical axis.
We learned that as you add mass to the top magnet, the distance between the magnets decrease.
And the graph helped us see that as the magnets come closer together, that the magnetic force becomes really strong.
That's why we added 4 washers per measurement when the magnets got closer together.
We also made our own maglev train.
We hope that you have enjoyed our experiment.
Goodbye from Golightly Educational Center and the Society of Women Engineers in Detroit, Michigan.
If you would like to learn more about higher class and get a mentor from the Society of Women Engineers, visit the NASA Sci Files website.
That was awesome. I may have been a bit hasty in predicting the demise of the train.
It's really cool technology.
I just wish Dr. D and the gang were on a maglev train right now.
You're right. It's gonna be tight. Plus, I'm a little concerned about the assignment.
Really? What was the problem?
Well, we learned a lot about the engineering method of research, design, testing, and redesign, but I'm not sure that will really help us figure out how transportation will look in the future.
True, and on the NASA Sci Files website, you can play an online game to learn about the future of transportation. But we do have a few ideas. Maglev trains, concept cars, and what about NASA's HyperX?
That's true, but I still think we need to do more research.
Well, NASA's probably the best place to start.
Did someone say NASA?
So what's up? Will the Treehouse detectives make it to the awards ceremony on time? Have the detectives done enough research on the future of transportation? Will they find Mr. Gregory? Stay tuned for the exciting conclusion of The Case of the Radical Ride.
Don't forget to look for the answers to the following questions. How will pave benefit travelers? How will tourism change in the next 100 years? Why does NASA want to inspire the next generation of explorers?
How's the internet connection holding up?
Good. As long as we're near a Wi-Fi network, we're in great shape. Why?
I'm thinking our only chance to make it on time is jetpacks.
Jetpacks?
Jetpacks. That's the answer. Look it up.
Hate to burst your bubble. That technology's been around for years, but it never became practical or safe.
Desperate times call for desperate measures.
Jacob, you're going too far. Besides, Bianca told us that NASA has some really interesting options for personal transportation.
Really? How does it work?
Not sure, but RJ is headed there now. I'm sure he can help us.
Oh, hi, you must be RJ. I understand that you want to learn more about personal air vehicles, or we call them PAVE for short.
Yes. Our class assignment is to try to determine what transportation will look like in 100 years. Now, from what I know from the PAVE, it sounds like a project of the future. Is it actually a flying car?
The basic idea behind PAVE is not so much to make a flying car, but to make an air transportation system with many of the same characteristics that we really like about cars.
So how will PAVE work?
First, we need an airspace system that works a lot more like our highway system, with small airplanes that work a lot more like our cars.
How do you build highways in the sky?
There are already 5,000 airports, and many of them are hardly used. The Small Aircraft Transportation System, or SAS for short, is working on low-cost electronics in order to give even the smallest of these airports all-weather capability. These small airports could then be safely used by anyone who'd like to fly instead of drive.
Sounds great. What would a personal air vehicle look like?
Well, we have several concepts that range from mild to wild. On the mild side, it looks a lot like small airplanes of today, but with some big differences. For example, there will be a ducted fan instead of a propeller and engine muffling. Both will dramatically help to reduce noise.
Now I know airplanes are really expensive. Will I be able to buy my own PAVE?
It'll be more expensive than a car, but less than an airplane, and that's because it'll use a lot of car parts and have a streamlined design.
Aren't planes difficult to fly?
Right now we have robotic airplanes that do most of their flying without help, but they're not that reliable.
So what's the wild PAVE going to look like?
Well, it's called our gridlock commuter, and it looks like a great big duck that carries 1 or 2 people. It doesn't go very far or very fast, but it only needs the space of a baseball field to take off on land, and the best part is that you can drive it on local streets.
Why does it need to drive on the streets?
To reduce what we call intermodal delay.
Intermodal delay?
Yes, intermodal delay is the time we spend going from one mode of transportation to the other. For example, today we drive to the airport, park, walk to the airplane, fly, and then reverse the process. Wouldn't it be nice if you could just have your airplane take you the whole way?
It sure would. But of course we couldn't fit an airplane in our garage.
No, but you could live in a community that centers around a small airport, and all of the houses would have a hangar as well as a garage.
Is that what transportation's going to look like in 100 years?
Actually, they already exist. There are at least 6 air parks here in Virginia now, and there are many more across the United States.
Wow, that's awesome. Are there any other benefits to PAVE?
Yes, PAVE makes it possible to have more choices about where to live, work, or go to school. Studies have shown that most people are unwilling to spend more than a little over an hour commuting. Before cars, you could only go a couple of kilometers in an hour. But with modern cars, you can go 40 or 50 kilometers in about the same time in heavy traffic.
We're learning a lot about traffic. Dr. D and a couple other treehouse detectives are still stuck on the highway.
With a PAVE, that problem would be eliminated for the most part. You would also be traveling at faster speeds than driving, and there'd be a reduction of intermodal delay. All these things would allow you to live 95 or more kilometers away from work, which would make it possible for you to enjoy both an urban and a rural lifestyle.
That's awesome. That means I could live near my grandma in the country and still work in the city. It sounds great. How soon will PAVE be available?
We're hoping to have a full-size flying demonstrator by 2010. After that, it could be as little as 2 years for a manufacturer to put them in showrooms right next to old-fashioned cars, so maybe by 2012.
2012? That's a lot less than 100 years. Leave it to NASA to be on the cutting edge. Thanks, Mr. Hahn.
You're welcome, and good luck, and don't hesitate to call me if you need anything else.
All right, bye.
Bye-bye.
Okay, so let me get this straight. You want to learn more about the future of transportation?
Correct. We thought we would go directly to the NASA website for more information.
Well, that's a great place to start, but I may be able to help you out.
Really? That would be great. You must know a lot about NASA.
Actually, I have a colleague who works for NASA. He could tell you a lot about the future of transportation.
That's awesome.
You know, his name is Terry Hertz, and he's helping NASA shape the future of transportation. You know, you could dial him up if you would like to. Is this wireless?
Yes. Here he is on the website. Hi, Mr. Hertz. We're the Treehouse Detectives, and we're working on an assignment on the future of transportation. What's your vision of how people will travel in the next 100 years?
Great question. I think people will be able to travel anywhere at any time.
Wow, how will they be able to do that?
With sonic booms no louder than background noise, supersonic aircraft will dramatically reduce travel time. Flights will be affordable, absolutely safe, and you can fly to anywhere in the world in a day.
Do you think there'll still be a need for an automobile?
There will always be a need for cars, but personal air vehicles will replace some of the car trips we take today.
Will there be any larger forms of transportation?
There might be air taxis. Then we could visit friends and family more often.
Do you think people will travel into space as tourists?
Definitely. Tourism today is about seeing the wonders of the Earth. And imagine tomorrow, seeing the wonders of the solar system up close.
How will we be able to achieve so much?
NASA's greatest strength is its scientists and engineers. They know no bounds to technology advancements. And strong partnerships among government agencies, industry, and academia will complement this anything is possible attitude.
Do we have any limitations?
We are only limited by our imagination and vision.
Thanks, Mr. Hertz. The future sounds so exciting. I can't wait to be a part of it.
You're very welcome. I know you and the other Treehouse Detectives will make significant contributions to our future. Call if you need anything. Bye.
Bye. That's great.
It sure is, and I sure am glad that Mr. Hertz was helpful.
He sure was. Thanks for the help.
Is there anything else I can help you with?
Well, we're really hoping for a chance to meet with Mr. Gregory.
You know, the Deputy Administrator of NASA.
He's one of our heroes.
Do you know him?
Well, I've spent some time with him.
We better get inside.
Maybe you can point him out to us.
Maybe.
Well, I've got good news and bad news.
If the bad news is any worse than missing the award ceremony, missing my brilliant acceptance speech, and missing my one opportunity to meet Mr. Gregory, I'm not interested. Give me the good news.
Sorry, Jacob. There is nothing I could do. If only I were in my Hummer, things would have been different.
Hummer? Dr. D, you have a Hummer?
Only in my dreams.
Things will work out, Dr. D.
So what's the good news?
Well, Bianca made considerable headway on our assignment.
That's right. We're supposed to report on what transportation will look like in 100 years. And we know all about scramjets that can fly at great speeds and blended wing jets that can carry 800 people.
We also know more about maglev trains and cool concept cars.
And the channel tunnel shows us that we can aim high and achieve great things.
How is all this progress going to happen?
There's only one way, the engineering design process.
You know, the process of identifying a problem, brainstorming, and selecting a solution.
Doing research, developing plans, and designing and building models.
Don't forget testing and evaluation, and redesign.
And redesign and redesign.
How could we forget iteration? You've taught us well.
Congratulations, kids. We may not make this ceremony, but you've completed yet another assignment. Quite an accomplishment while stuck in traffic.
Guys, guess what? Bianca just sent us an email. The ceremony is being streamed live over the internet.
Are we connected?
Yes.
Dr. D, don't move the car.
Good afternoon. I'm Mr. Gregory, and today we are recognizing area students
for outstanding achievement by middle school kids. Throughout history, we have looked to the heavens for answers to life's bigger questions. As we stand at the threshold of the 21st century, we have the potential within our lifetimes to discover the answers.
Our first award is
Outstanding Achievements in Inspiring Others to Succeed in Math and Science. The winner for our first category, or should I say winners, are the Treehouse Detectives.
Quick, email Bianca my speech.
We won.
I really wish we could have been there.
Well, we'll be there shortly. Maybe you'll still get a chance.
I think you're right, Dr. D. More than you know.
What do you mean?
I just got an email from Bianca. You'll never believe what she just told me.
With the nation's new vision, a renewed spirit of discovery, we're going to be building a new crew exploration vehicle. We're going to be going back to the moon. And we are going to send humans and robotics to Mars and beyond.
I can't wait. What can we do to make this a reality?
First of all, you have to stay in school and take lots of courses in math and science, and check the NASA website. See if there are any areas of interest that you might have, and just begin to prepare yourself for the future.
Sounds just like the steps we use to solve problems.
What is NASA doing to inspire the next generation of explorers?
Well, you know, education is a core part of NASA. But what we're trying to do is make science and discovery and technology exciting for you. You know, one of you might be the first to step on Mars.
Thanks, Mr. Gregory.
You know, I actually have a question.
Just ask.
Where do you all do this exciting research?
Well, it's your backyard.
It's her backyard.
This is a big backyard.
This is my backyard.
The NASA Science Files was made possible through the generous support of Busch Gardens Williamsburg, SeaWorld, and NASA Langley Center's Aerospace Vehicles Technology Office. Captioning provided by NEC Foundation of America.